Ladies and gentlemen, welcome on the first and only talk on our afternoon session. Our speaker is Haitang Yang from Sichuan University. He's working on gravity, and he's going to talk about how Einstein gravity emerged from quantum entanglement entropy of CT in d dimensions. Please join me to welcoming our speaker.
Okay. Okay. And first of all, I thank you for staying until the talk and give me this opportunity to share our work in the past 1 year with you. And I promise this talk would be very easy and totally accessible for graduate students. We will have a easy life. All right. I'm very happy to meet some old friends here, especially Armin, my former advisors. All right, this is the outlines, and this talk based on those works in last year. I think we finished, and some work will appear very soon. And my collaborators, one of them is Sichuan University, and Xinjiang is my current PhD student. And I will, this one would be very short because I don't want to spend too much time, that time limitation. All right, let's first say holographic. We all know that holographic principle, so I won't spend time on this. And inspired by DSFT and black hole entropy, Yu and Takalagi proposed this one. The entanglement entropy of safety D equals the dual minimum surface area in ADS with y extra dimension. And the minimum surface, this is the entanglement surface, A entangled with B. All right, and this dot is ADS1. Use this formula. What should be emphasized is that in the original proposal, the RT formula is for adjacent entangled region. In adjacent means A and B they are adjacent, it's continuous. And in three-dimensional geometry, the RT surfaces are geodesics. We will see why I emphasize this. All right. Okay. The question, the nature, okay, this is very general, nature of gravity. We know that from general relativity, gravitational force is an illusion of space-time curvature, which is realized through Einstein's equation. About 10 years ago, there is a new interpretation. We have some shift understanding of gravity. It says that space-time structure emerges from quantum entanglement. So space-time structure, it looks like illusion of quantum entanglement. However, how to realize it? That's the problem, right? When we say how to realize it, the first step would be, can we extract the metric or even Einstein equation, the dynamic equation from quantum entanglement explicitly? All right, this is the big motivation. Let's say some more specific things. What I just said, RT surface in three-dimensional is simply geodesic. We all know that given a metric, we know how to derive geodesic, right? For 82 points, the geodesic length. However, there is also a simple way to extract the metric from geodesics. How? Let's say given a metric, we know how to calculate the geodesic distance between 2 points. Then we know that geodesics are defined with parallel transportation, which means the tangent vector of the curve is parallel transported along the geodesic. Therefore, this is scalar and constant. This is because scalar, so quantum derivative becomes ordinary derivative because it's constant along the geodesic. So, okay, like this. Therefore, we can define since word function. This one was in literature, I think, many years ago. It's a scalar of x and x prime, which is defined as 1/2 L squared. This one, so we just integration we just said that this is the constant or not the geodesic, right? So we can move it outside the integration. Therefore, we got this one and perform this integration simply t squared. Of course, the parameter must be like some more fun parameters. When it's very sharp, I mean the points are close to each other, which means t is very small. In this case, we can use t squared cancel d tau delta tau, right? We're only left with this as t goes to 0. Therefore, we say that very simple. We derivative and take a limit, we got g mu nu, right? It's like this. So g mu nu, when you derivative for x and x prime, you will get yx to minus sign. This is y equation. And if you derivative for the same point, because this is vector, so this derivative would be some like covariant pure. However, when we take the limit, this one also will become ordinary one. So this is not important. In any case, we can calculate the metric from given geodesic distance with either of them. And with the notation that a bracket denotes the limit, which means we take x prime to x, right? And the indices inside the bracket, the constant limit is just derivative with respect to x or x prime. This is a notation. We will use it in later parts. Note that end of geodesics must be arbitrary to cover the whole geometry because we want to get the metric in the whole space, right? So the geodesic should not be constrained. The ends can move freely. No, this is not something. This is some result obtained a long time ago. But yeah. Yeah. But when you take the limit, there is no difference because the collection vanishes. But anyway, we will use this one. Okay. So our 2 point. Yeah. Yeah, for scalar function. Yeah. For you mean for that will become the covariant derivative in that case. All right. So this is something like in Soviet, right? This is like equation for non-scanner for say tensors, right? Because when we define the covariant derivative, we need a metric. So it's more or less like solve the equation. All right. All right. So we will some identities for the sense word function. Then we just define this one, 1/2 L squared. This is we'll just present it. All right. This is how to get the metric from geodesic length. All right. So this one it can be proved. This one is correct. Therefore, we just contract because this one you see this one the coincident limit and and the derivative commute. So this one basically is that you contract with the indices. We define this one. It turns out this quantity is just 1/3 of rich tensor. And then contract again, this quantity is 1/3 of rich scanner. Therefore, we can write the versus Einstein equation, right? This 1/3 just comes from here. So this is geodesic versus Einstein equation. We're going to use it. On the other hand, we just said in three-dimensional geometry, coordination to RT surface are simply geodesics. And RT formula says that geodesic equals entanglement entropy. So one immediate question is, can we use this equation to write the Einstein equation in terms of entanglement entropy, right? Two-dimensional, 72. Can we? If we can, means that we can derive Einstein equation from safety 2 entanglement entropy. Be careful, safety 2, two-dimensional. We will see it. So, got questions? The first question, can we write three-dimensional Einstein equation in terms of safety 2 entanglement entropy? With that equation we just show. Because we know how to calculate safety 2 entanglement entropy in field theory. We know this. Long time ago, I think 31 years, it's published 1994. All right. If this answer is positive, then we would ask how to generalize to higher dimension. Why we care about this? Because we know that three-dimensional gravity is topological and locally trivial. Some conclusion get from three-dimensional gravity may not be universal, right? So that's why we care about higher dimension. This is highly non-trivial. Well, in order to get this one, we have to face two big challenges for higher dimensions. The first one is this. We don't know how to calculate entanglement entropy for higher dimensions. Over 30 years, no one knows how to do it. We only know how to calculate it in 2 dimensions. So this is the first problem, persisted over 30 years. And the second problem is this. Intuitively, we know that the RD surface in higher dimension is hypersurface, but not geodesics. For geodesic, we can use the geodesic version of Einstein equation to write down the Einstein equation in terms of the entanglement entropy immediately. However, how can we get metric from the hypersurface? Mathematically, there is no general method to do this. So, looks like two obstacles. We are going to solve this problem in this talk. All right. As said, the question one, can we write this three-dimensional Einstein equation in terms of safety to entanglement entropy? Well, we need to go back for the adjacent entanglement region. Usually, this one in literature termed as pure state, such as this one. This is safety 2. We take 1 times less t equals t equals 0. This is safety 3, right? And you see the entanglement region are labyrinth. Okay, they are continuous. So we say adjacent. The entanglement entropy, this one must be divergent from QFT. We know that, right? Because the intense short-range correlation in the neighborhood of those points. All right. It turns out, okay, this is result. Say for this one, we don't know how to calculate this one. All right. But for this one, we know how to do it, and the result is simply this one. So this is central charge. This is the length of this entanglement interval, and this UV cutoff is divergent, right? So this is divergent. All right. Let's say it's holographic dual. The holographic duality of this entanglement entropy in safety 2 is just this geodesic, which ending on the boundary of the entanglement region. We know that the metric of ADS3 is this, right? When you go to the boundary, the distance here, you will get a divergent quantity. So we just calculate the, okay, we use this result, L much larger than UV, than this epsilon. This is also a cutoff. Under this is exact, all right? This is exact result for geodesic length in ADS3. But when L is much larger than epsilon, it approximates like this, all right? Or we apply to this. So this one exactly, not exactly, right? It equals the entanglement entropy in safety 2 we just showed in last here, all right? Here, they equal. Okay, this is the original version of RT formula. Then the question, can we apply this one to get the dynamic equation of entanglement entropy now? The answer obviously negative. Why? Because both of them are divergent, right? And the geodesic is special. It's ending on the boundary. We need to differentiate on two boundaries of the geodesic and then take the coincident limit, right? However, because they are ending on the boundary, you can never get a metric at this point. You can always, because you make them approach to each other because they are attached on the boundary. Therefore, it's only a special class of geodesic attached on the boundary. On the other hand, both sides are divergent. It's on some particle relation, not some exact relation. So we cannot be able to derive the Einstein equation in terms of entanglement entropy. All right. How to do that? We are facing this challenge. So divergent entanglement entropy, and we don't know how to calculate the entanglement entropy for higher dimensions. And for the minimal surface in higher dimension, a lot of geodesic about higher surfaces. Our question, we ask this question. All right. Is it possible to find some finite elementary entanglement entropy? Because we just said the entanglement between adjacent region is divergent. Can we find some finite one? Is it possible? This is the question we ask. All right, this relative entropy, mutually, they are combined quantities and not elementary, so we don't care about it. And there is a theorem, the Ricci-Leiter theorem, which says any two regions in QFT are entangled. Well, this is a hint. Then let's ask, how could it be possible the entanglement entropy be finite? In order to be finite, the entangled region must be disjoint, right? Once they are adjacent, we know that entanglement entropy must be divergent. So in order to find that entanglement entropy, the entangled region must be disjoint. On the other hand, we only know how to calculate entanglement entropy for pure state. For mixed state, we don't know how to do it. Therefore, in order to be able to calculable, the entangled region must be mutually complementary to form a pure state. So we need those two satisfied. We will see if it's possible to find such configuration. All right, this is just the brief review of how we calculate entanglement entropy by path integral in 2 dimensions. All right, this is definition. All right, we have some Riemann surface sigma where safety lives, and this wave function on that sigma. And so the total density matrix is defined as this. And this is reduced because we want to calculate the entanglement entropy between A and B, A and A bar, the complementary part. So this is reduced density matrix, which is obtained by trace out A bar. And then this is definition, von Neumann entropy of the system. However, for technical reason, this one, we don't know how to calculate it. So therefore, rather than calculating SA directly, we use the Riemann entropy. All right, Riemann entropy is defined as this. Okay, you only need to trace rho A to the n copy, and take the limit n goes to 1, we will find S equals S1. All right, so we calculate this one. How to do that? For 1 plus 1 infinite system, we use this as example. The density matrix of safety is simply obtained by a cut. Okay, this is Riemann surface where the safety 2 lives. The density matrix, in order to get it, just cut it along AB. Okay, we calculate the entanglement entropy between A and B. We cut it and split it as 2 parts. All right, as 2 parts. And this is so you say this density matrix. And we want to do the trace, we glue them back again. So it's quite simple. You glue back, you trace means. All right. So this is trace. Of course. So when we trace when we glue back, this is we perform path integral on this one. Of course, this is the partition function, right? So this you will get 1. All right. We just see the picture. We don't need to care too much about this expression. All right, it's very simple. All right, we need to calculate this one, right? Rho to this. All right, let's see how to do that. All right, this is our total density matrix, right? Cut open along A and B. Then how to get Rho A? Rho A is obtained by this way. We glue B, but leave. All right, here is still cut open, but B is glued. So we got a Riemann surface like this with a slit here, open slit here. So this is Rho A. All right, and Rho A to the n is obtained by cyclically gluing n copies Rho A. So this one, the upper edge glued to the lower edge, and this one, blah, 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 and cycling like this. Well, this one is not important. You can ignore it if you don't like it, because we are not really need to use this. But just show you it's complicated to calculate. Use this is replica trick, the standard one. And then after we got the Zn, and then we can just perform path integral on this one. Zn is path integral, the partition function on the replicated manifold we just produced. And Z1 is just one copy of this one. So, all right, this is a formalization. We just need to, so basically we need to calculate this one, Zn and Z1. All right. However, we know that when we glue this, we see at the end points we got conic singularities, right? Therefore, the calculation is highly non-trivial. And I think Carly did a lot of work on this. The problem is this. This is for dimension equals 2. How about 2 higher dimension? It looks forbidden. That's why this was not done over 30 years. All right, let's come back. Our question. Is it possible to find some finite elementary entanglement entropy? Two conditions. Entangling region must be disjoint and must be mutually complementary. Is there such configuration? Yes, we do. This one. All right. The annular safety 2 precisely has those two properties. We want to calculate the entanglement entropy between A and B. AB definitely disjoint. At the time t tau equals 0. Be careful, the tau is upward time. Oh, any other time, we just choose this for convenience, not special. For tau equals 0, we say that A and B, they are complementary, right? They compose the whole system. It's a pure system, pure state. Therefore, we can calculate the entanglement entropy easily with this one. How to do that? Well, let's see. Use replica trick. We want to calculate between the entanglement entropy between A and B. Like we just said, we first got the A, right? In order to get the A, we glue B and let A open. This is the A. And then we glue cyclically n copies of the A, right? Just this one. One by one, one by one, one by one, you glue. So we still got annulars, but with the period 2n pi, right? So we calculate the entanglement entropy. We just need to calculate this one. Zn is this one. Calculate the entanglement entropy, partition function on this one. This is just the annulars with 2n pi, period. And Z1 is just this one. All right. So quite simple. It becomes even trivial to calculate the entanglement entropy. All right. In this paper, and this for static one, this for covariant one, we did the computation. Actually, this one was calculated by Carly long time ago, 20 years ago. We just used his result directly. We don't need to do it again. And well, we found, okay, this one, of course, it's finite. And it's adjacent limit. So you take a limit, say, like the inner radius to 0, outer radius to infinity, you will get AB labeling, right? Adjacent. You will get adjacent limit. You will find the divergent adjacent entanglement entropy. This one. I use blue for adjacent and red for disjoint. All right. So the previous adjacent configuration just the special limit of this more general disjoint configuration. And this one is finite. All right. Actually, this one can be equivalently interpreted as the mixed state in the infinite system. Say here we want to, how about the entanglement entropy between A and B? For 2 dimension, we'll say like a finite temperature is just the finite cylinder, not an infinite cylinder. All right. So this one, so you know, our original purpose is not calculate this one. Our original purpose is to calculate mixed state entanglement entropy between A and B. People usually use purification by adding some other auxiliary system inside it to this system to purify it. But what we did is this, okay, because we are care about the entanglement entropy between A and B, so there must be some universal quantity only depends on A and B, or it doesn't make any sense to talk about entanglement entropy between A and B, which means it's totally independent of C and D. Then why we just not the subject C and D? Remove it by disk. I use a disk to remove C, use a disk to remove D, you see? Just got this one. So this was an intermediate step in our original work, in this work. Subsequently, one day we suddenly realized we should take this one as the fundamental framework. What's magic is next slide. Once we treat this one as fundamental, all right, you see, can easily generalize this to higher dimension, right? All dimensions. Once take this as the starting point, this 2 dimension, this 3 dimension. For higher dimension, becomes a ball, right? The section becomes a ball. So by this simple converting, we got general higher dimension one. So critical insight is that we can suitably generalize annual safety to higher dimension on this solid torus. You see, the replica of the solid torus is still very simple, right? We just glue this one and replica with this one. You got another solid torus, but simply with period 2n pi, right? So there is solid torus. As Z1, the only difference is that the period is different. So what we left, we only need to calculate partition function on the solid torus for any dimension. All right. So let's see how we did it. We only need to calculate partition function on this one. Well, this one lives in a flat space. All right. It's in the flat space with this metric. In order to calculate the partition function, we realize it's periodic. So we can treat it as a thermal system. For zeros, we first, because it's conformal field theory, we can make a Wills scaling by this one. And the metric becomes this, right? And then this one becomes we can treat theta as the time now, equivalently. So this thermal system and the partition function is simply this one, space. And H is the integration of the energy density on this A, but with this metric. This could, all right? So for replicated n copies of B, we just replicate it like this. And the metric is this, and of course it's quite easy. Just there is an extra n here. Still a thermal system. And the relation between Hn and H is 1 over n squared. And the entanglement entropy, the calculation is trivial. We just do this, right? And so they on this n copy replicated and with the original one, and we got this one. And this finally is quite easy. You take n to 1, got this. Okay, the Hamiltonian expectation value on this A, area of A, the volume of A, but with this metric, okay, without n here. So quite easy. We got this one. The disjoint entanglement entropy between A and B becomes this one, this integration. And this is Casimir energy. All right, the vacuum, because we only care about the ground state entanglement. So usually it's negative. So the volume, we just perform the volume, right? The n-dimensional ball, that's quite easy. And so this is the result we got. This entanglement entropy between A and B. Quite easy for any dimension. However, we say that this case A and B are symmetric, right? But we'll care about some arbitrary case, not just symmetric, of course. So we'll just below to that, the disjoint is proportional to scaled volume. You see, this is volume. That is we imagined. We always that entanglement entropy proportional to area. but you say it's a scaled volume. We will see the area law later on, all right? But not the area of the entanglement region. We will see what happened. So when A and B are not symmetric, or even in more configuration, let's say, usually we have these two configurations, right? This is just, okay, you look at the, from up, downward, you look at this one, you say A and B. And this one, A and B with the different reading. And this one, A inside B, this cavity configuration, this is juxtaposed configuration. We know that this is the conformity for configurations with two spheres. It's defined as R square plus R prime square minus this one, the centers. And this one, with the same inversive product, they are conformally equivalent. All right? So this one classify all equivalent configurations. These two conformally equivalent if they have the same inversive product, which means we can use conformal transformation to transform this one to this one, and even for this one, right? Okay. Yeah, for this one, okay, even. As long as they have the same inversive product. All right. So we just calculate this one. We write it in the conformal invariant form. All right. So this is we just calculate for symmetric case, and we write this one as inversive product, which is conformal invariance, and we plug this one into this. So this is our final result for 8-dimensional entanglement entropy in safety. So it's expressed as inversive product. All right, the inversive product, once again, is defined in this way. All right. So this works for both cavity configuration and juxtaposed configuration. So immediately we will imagine, can we reproduce the adjacent configuration? All right, like this, right? We are familiar with that. The epsilon goes to 0. That case, okay, above entangling with the rest of the region in any dimension, right? This is people usually care. They are concerned. Well, this is just the special case. So the inversive product, we simply calculate it. It's like this, expressed this one. We take a limit, epsilon goes to 0. We got the inversive. Usually people said the pure state entanglement entropy in one dimension, like this. All right, we just list some of them. So this one is the familiar one. For this one was calculated a long time ago, but all this cannot be calculated before. All right, now we know it. It's for order dimension, it's the exam. For even dimension, we have some order of the epsilon. All right, this is result. And this match, we can calculate this by RT surface, right? The holographic RT surface. And they perfectly match holographically. But we calculate in CFT, right? We didn't use holographic. No CFT, no holographic mentioned. All right. And our calculation is also shape independence. We just say, okay, for A and B, this symmetric with some shape, and with the shape is X, the volume of X, and we just showed that this one is always correct. So for any shape, A and B, so this works. Of course, this one is calculated with this conformal metric. All right.
Where is the dependence on the shape of this region showing up? Is it effect or where?
Oh, you mean what?
Where is the dependence on the actual shape?
Oh, just this one.
Sorry, I missed.
Oh, X. Oh, X is just say for some arbitrary shape. No. The shape of A or B.
Shape of A or B.
Yeah, they must be the same in this.
But that's, is this the area law or?
Yeah, you see this. Okay, this is for this joint one is the volume law, right? the area law, it's got when you take this adjacent limit, it becomes an area law here. So area law is some special case. Only in the limit you got area law, but for generic case, it's still volume law.
Here, in general, subleading terms, but in the formula that you described, there's no subleading terms at all.
What?
So in the area term, there is leading order in area, and then there's some subleading order in area.
Yeah.
But in the expression that you just
No, because that's the exam. The disjoint one we give the exact result, and you take a limit. You got this one, the usual one we are familiar with is just a limit of the disjoint one. Okay. What we give this? Okay, this is exact result. There is no limit, no UV cutoff from that, and it's totally exact. And then you consider this special configuration. You take the limit, epsilon goes to 0. You expand it, you found this. The same, given for sphere, it's also the volume. Here. Yeah, it's for volume. Volume. Huh?
So there is this in the case of balls, there are non-trivial geometric functions there.
Yeah.
We were saying that why is it that we're not get some non-trivial?
You will get some other. You will also get a formula for the C. That's very subtle. We can discuss later on because for arbitrary shift, in most of the cases you may not get an analytic expression, but you will get a numeric one. Yeah, it's one. Even for sphere, it's one. I just said this is surprising. Okay, the familiar area one is just the limit, but actually it's one. Okay. All right. We can discuss later on. Oh, sorry. All right. And because I need to show the Einstein equation, how the Einstein equation emerges. All right. So also the RT formula becomes naturally emerged. We say that the time entropy is proportional to a volume. Okay, this is not area. Sorry, it's a volume defined with the scaled hyperbolic metric. This is precisely this one is precisely the area of this one, right? This is RT formula. So RT formula becomes manifested here. This you see the difference is that the original RT formula is an equality between two asymptoticity, but here both sides are finite. So we say it's the exact version of RT. All right. Okay. We want to see how we got Einstein equation. We now turn to derive Einstein equation from entanglement entropy. Okay. First to say we have these two. We use those parameters. It's free to choose other parameters. Okay. We just use this one for convenience. And we will write our general equation for the disjoint entanglement entropy in this form by Casey, right? Right down in this form. Let's see. We just said, okay, we just said the entanglement entropy between those two is finite, right? What's holographic do? We said in safety 2, it must be some geodesic. We say, okay, it's just this one. You will find it's easy to verify exactly equal. All right. In safety 2, it is 3. So it's entanglement entropy exactly equals this geodesic length. All right. Geodesic length, we know that because we know it satisfies this Einstein equation, right? So we immediately use this one, plug in, write down the Einstein equation in terms of safety 2 entanglement entropy now. Because it's exact. Plug in. All right, this is for safety 2. How about for higher dimensional safety? All right, this is a little bit tricky. For higher dimension, we just do it in the general dimension. For convenience, we reparameterize success of I and introduce this. This grouping, I think, is non-trivial. You see, Xi has the dimensionality of Xi is D, and with an extra dimension. So this each of y mu and y mu prime are the dimensionality is d plus 1. All right. So this they can be viewed as points in d plus 1 dimensional geometry. Just then we can define some metric like this. This is still a coincident limit y prime to 1 and derived like this. And we define a chi here. All right. You can ignore that this is just Newton constant. And with this, it looks complicated, but they just imagine d equals 3, d equals 2. When d equals 2, this one 1/2 s squared, right? All right. So for this one, we just plug and then define like this. Plug in, define. All right, definition. This is just simply definition. All the quantities are defined in terms of entanglement entropy, right? We didn't say anything about geometry, just entanglement entropy. Then you can verify this. All right, all of the quantities in terms of, because you see chi in terms of S, entanglement entropy, G mu nu in terms of entanglement entropy, and R in terms of entropy, and then you found this equation, which is precisely Einstein equation in d plus 1 dimension. Okay, with this lambda, the cosmological constant in this one. Okay, so we write Einstein equation in terms of safety D data, but of course it's vacuum solution, vacuum version. All right. Intuitively, how do we interpret in higher dimension? Basically, it's like this. Just when we calculate the entanglement entropy between A and B are two balls. To determine a ball, we first fix the center and then the radius, right? We need d plus 1 parameters for one ball. For two balls A and B, we need double d plus 1 parameters. Those parameters precisely fix 2 points PQ in d plus 1 dimensional space-time. It fixes this one, it fixes the geodesic. And the geodesic in turn fixes a minimum and a minimum disk, then fix a minimum ball, blah, 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 just like this. That's why. All right, just be careful that the distance between PQ in ADS is like this, all right, log of L2 over L1. So you see our entanglement entropy actually determined by L2 over L1. It's precisely determined by the distance between PQ. That's why we can do it. We spent over 1 month to interpret what happened here. All right, so this power is easy to understand because just imagine the dimensionality of this surface. Okay, this is the entanglement entropy, but the holographic deal of this one, it's a hypersurface, right? The dimensionality of the hypersurface, the arctic surface is d minus 1. So this is d minus 1 cancel, and you got square here, all right? And when you take this limit, and we only left with the quadratic term. This one has not been unknown yet. Will appear very soon, all right? So for this is, we can get the Einstein equation in higher dimensions. All right, this one, I don't want to spend too much time on. You say you already very easy because we got the metric from entanglement entropy, right? So for the ER equals EPR, it becomes straightforward. We just calculate the entanglement entropy between, you need to be careful to select those between them must be disjoint, right? The entanglement entropy must choose some disjoint intervals. And we calculate the entanglement entropy between those two safeties and plug the entanglement entropy in here and just use this one, you will immediately get, you found this d mu nu. It represents the wormhole. Just use this formula. Quite easy, straightforward. That's why I don't want to spend too much time on this one. And the details with this one, we may make some modification in the future for this one. Not been submitted yet because we still have something to add. All right, but this is summary and discussion. I want to control time. I don't want to, because we have some ceremony. Okay, we provide the general framework to compute the entanglement entropy in CFT-D, all right, for general dimension, and the explicit expression for bullshit to the entanglement region is given. And we demonstrated how to derive D plus 1 dimensional Einstein equation from D-dimensional safety entanglement entropy. All right, for safety 2, the RG equation I promised in the abstract submitted for the conference, but I totally ignore here. In safety 2, you will find the RG equation is exactly a geometric identity, but and this one is presented in this paper, right, for the details. And we just showed the ER equals CTR details in this paper. And this crucial definition. From this, okay, we see, this is what I want to say. G mu nu is defined by entanglement entropy, right? Two derivative and take limit. In this case, G mu nu is not fundamental quantity from a quantum quantity, right? What we know chi is entanglement entropy it's a quantum feature, quantum quantity from theory. It's already quantized result. And the G, the metric is derived from it. Why quantize it again? Why? We usually say how to do quantum gravity, quantize G mu nu. But from here, it looks like it may not be the metric. Also, because it's some double derivative on chi, we say that gravity is non-reducible. Well, just say like Klein-Gordon field, this one is renormalizable. If you define a new field with this one, of course it's non-renormalizable. And so we say that the cosmological constant is also a derived quantity of entanglement entropy. It's not some independent one. All right. And the disjoint, I would say it's a general entanglement entropy proportional to the volume of the entanglement region. The usual area law of entanglement entropy of the adjacent configuration is simply an asymptotic property of this one. All right, this one is okay. The usual area law is the property of adjacent entanglement entropy. This is a limit of this one. All right, this is more general. Also, the non-local duality between boundary and bulk is explicit here. We know that entanglement entropy is non-local, right? In field theory. Well, but the G mu nu is local. So the local and the non-local duality is explicit in this mathematical expression here. Moreover, that once this one is not analytic, you make derivative, you will get some singularity here, right? So when cut, which means that phase transition probably the singularities in time, if we interpreted the geometry does emerge from quantum entanglement. This just means that space-time singularity probably just some different singularities, different phase transitions of the quantum entanglement. The question which makes me suffer right now, and we are struggling, is how to extend this method to QFT. For QFT, we can carry the symmetric case, but for general case, I don't know yet. We are struggling on this. And this one is introduced and will appear soon. And we found this framework. We know that for the algebraic QFT operator formulas, there is no, the only, and not only, the largest problem of the algebraic formulas is that cannot give you specific entanglement entropy. It cannot calculate. We cannot not do calculation with it. But this one we found it. We can solve it. We can solve this problem now. And this one is we are writing the draft right now. All right. And also, I don't know if there is any other, but as far as I know, the disjoint entanglement entropy is a unique physical object on both sides exactly equal, not asymptotic. All right, this is my talk, and thank you all. Sit down for the last one. All right.
Questions?
You have an expression for the cosmological constant.
What?
Cosmological constant. So can you get a right order of magnitude for the observed cosmological constant?
Oh, you mean cosmological constant, right? This one, right? Your question is.
Can you get, so there is a problem that the computation using methods of quantum field theory are very far off from the observed values.
I don't know yet. I have no time to consider problem yet. But that's sounds very important. Yeah, we need some more. This is just some like interpretation or conjecture. We don't know, but mathematics tells us this. Of course, we need to do more specific calculation, and especially cumulative one, right? For cumulative one, we will get some very non-trivial things inside that case.
Anyone?
Okay.
I'm a bit confused. Is it that this G mu nu would always satisfy Einstein equation?
yeah.
I see. Then there's no requirement over large central charge.
Oh, it has, because we only care about ground state. Implicitly taking large limit.
Why large limit?
Well, in 72, we say it's very easy because when we take C goes to infinity, you are only left with ground state entanglement there. You will find we calculated and we found everything, and when we take large C limit, only ground state left.
Lots of CFT for any CFT, I go and take the ground state, go compute entanglement entropy. The corresponding G mu would also satisfy Einstein equation.
Only ground state. I can only say.
All right, but that's for any CFT,
Yeah,
not
any
necessarily
CFT.
with large central
Yeah,
charge.
I don't care about the details.
So central charge corresponding metric that I can read off from it, large central charge or small central charge, they will satisfy Einstein equation. That is a statement that you make, isn't it?
I don't. I just said that okay, in safety 2, we have only one central charge, say, right? For higher dimensional, I don't know what you say, like 4 dimension, we have say A, blah, 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 and other. So that's why I only care about ground state. yeah, ground state of ether. It looks so. Say again.
Second, not exactly Einstein gravity.
For higher derivative, I think we need some more. I mean, no, this is only for safety, right? Yeah, I know, but that's a question actually puzzles me. I discussed with Ami. I want to ask one question. We have so many CFTs, right? Even in many CFT, you only say ADS CFT, it just corresponds to one geometry. Okay, the geometry could have like ADS 5 times S, blah, blah, blah. Yeah, but here it looks so. Okay, I only trust the mathematics. Yeah. Right.
Probably a silly question. So, in the last part, you talk about the algebraic QFT connections. So, would it change anything? Like, I change QFT as a type 3 Von-Neumann algebra?
Yeah, QFT is highly non-trivial. For QFT, we found just a few days ago, when I discussed with you, we go back to think, and we found QFT for this case we can calculate. But there are some very funny things. Okay, for QFT, we can calculate the symmetric case. All right, just use Rendener space, blah, blah, blah. And however, for this is some special case, right? A and B symmetric. It's regular solid torus. But for this one, see, for this, we don't know. Because here it's crucial, we have a conformal invariant, right? Which means for different configuration, if they share the same conformal, share the same inversion product, they are conformally equivalent. So once we carry the symmetric one, we got those two, right? But for QFT, we don't have such thing. So even we calculate the symmetric one, we don't know how to calculate this one. We cannot use conformal transformation. That's the big problem. Yeah. That torture me right now, actually.
Okay, let's.
Okay.
Just to get one point, this 1D, we know we have this. No. So I understand conformal field theory, how to calculate the entanglement entropy with two separate A and B and
Yeah.
the replica.
Yeah.
I do conformal
Yeah.
mapping.
Right.
So also, I think 1D they do all kinds of things, use conformal mapping. So, but the higher dimension, I try to get to the point. Higher dimension, we do not have conformal mapping.
We have global.
Oh, yeah, we only have global.
Global.
But not,
Enough. We found that's enough.
that's enough for your calculation.
Yeah.
That's enough for
That's enough.
global. That's enough.
That's enough.
But 1D is more powerful, right? 1D, they can calculate anything. Or
Well, so one question here. Okay. In safety 2, right?
Yeah.
We can calculate the thermal by simple local conformal transformation to the inner, but here no. So for third, I don't know how to calculate it yet. Well, this is also a question we are asking right now. We are doing right now. Try to in higher dimension the thermal one. You can imagine once we got the thermal entanglement, the dual metric must be equal, right?
Yeah.
It's highly non-trivial. This is very important, right?
So you are trying to do them.
Yeah, I'm trying to do that.
Then do you rely? Then global transformation is not enough.
No, you cannot use global transformation to get the thermal from the t equals 0 case.
Okay. Yeah.
But here we only do the t equals 0 case, and
But the 1D you can do it. 1D.
Just do it by local transformations, right? Exponential map. Right. Okay.
Let's thank our speaker once again.
Okay.
It's the last talk, so we end our conference. Let me remind you that we have closing ceremony in the AM2. And thank you for your visiting us, and see you next year.